Let's jump right into this explainer. We're living through an absolutely massive technological revolution right now. But as we scale up artificial intelligence, we are slamming headfirst into a harsh reality. We aren't just bound by software algorithms anymore, folks. We are bound by thermodynamics. How exactly are we going to power the intelligence age without breaking the planet's physical limits?
Get this, by 2028, data centers are projected to consume up to 12% of the entire US electricity grid. 12%. That exposes a massive thermodynamic bottleneck. We're basically running out of raw power and the terrestrial infrastructure to actually support it. But to figure out how we push past this, we first need to look at the machine that's eating all this power. So, what exactly is the AI factory vision? And what does it mean to manufacture intelligence in the deep? To understand where all this juice is going, we have to look way past standard servers sitting in some IT closet. Nvidia CEO Jensen Huang really hit the nail on the head here. He says we're entering a phase of industrial infrastructure development on a scale humanity has literally never witnessed before. This isn't just a software update, right? This is the heavy industry of the 21st century, the AI factory.
It gives us a brilliant mental model. Think about it. Just as the Industrial Revolution used generators to turn physical motion, atoms, into electricity, today's AI factory takes those electrons and manufactures them into digital tokens. Electrons go in, tokens come out. And those tokens, they're pure intelligence, language, biology, physics, reasoning, all being generated by this brand new industrial process.
To really grasp the sheer scale of this, picture the new economy as a sort of industrial five-layer cake. Everyone sees the top layers, right? The flashy apps and the AI models. But beneath all that lie the computers, the physical infrastructure, and at the absolute bedrock, energy. The foundational roadblocks to our future are sitting squarely at those bottom two layers. Just consider the crazy physical density of this bottom layer. A single server rack in these new AI factories packs in 72 highly advanced chips. It weighs 2 tons, contains over 1.5 million individual parts, and costs a mind-bending $4 million. We're talking about arguably the most expensive piece of manufacturing equipment on Earth. And the economics behind assembling all these racks are just staggering. A 1 gigawatt AI factory might cost $50 billion to build, which is a massive capex, but it produces up to $400 billion in intelligence output. The return on investment is just so massive that capital will absolutely bulldoze any roadblock to get it built. The demand is practically infinite. But here's the catch. As we rapidly try to scale this massive token output, we're aggressively hitting the physics wall, the brutal terrestrial grid limits. Look at how we cool these machines down. This metric is WUSE, or Water Usage Effectiveness. It measures the liters of water consumed per kilowatt hour of power. Traditional land-based data centers are highly water-intensive. They can gulp down up to 4.8 liters of water for every single kilowatt hour of energy expended. We are literally evaporating municipal water supplies just to keep these racks from melting down. And then there's PUE, Power Usage Effectiveness. This takes the total power of the facility and divides it by the power used purely by the IT equipment. 1.0 is mathematically perfect, meaning zero power is wasted on overhead, like cooling. Terrestrial facilities are really struggling to maintain efficient PUE right now. The energy overhead is just way too high. So the industry is urgently searching for extreme off-grid environments. This search brings us to Microsoft's Project Natick, diving deep into subsea data and submerged intelligence. This is a breathtaking thermodynamic solution to the physics wall. What if we just put data centers at the bottom of the ocean? From a visionary white paper in 2013 to the Scottish deployment in 2018 and its successful retrieval in 2020, this timeline proves that taking compute offshore went from a wild guess to a proven reality in just a few short years. Just compare the two worlds. Up on land, you've got humans bumping into equipment, a highly corrosive oxygen atmosphere, and massive water consumption. But down in a subsea pod, it's a pristine, perfectly engineered environment. You get completely autonomous lights-out operation in dry nitrogen and a closed loop with absolutely zero water consumed for cooling. Zero. Because of this pristine environment, the results were honestly incredible. By taking humans out of the equation and replacing corrosive oxygen with dry nitrogen, the submerged Natick servers achieved an astonishing failure rate. They broke down at just 1/8 the rate of their land-based control group. That's an 8 times improvement in reliability simply by dropping the computers into the sea. The exact specs of this Phase 2 vessel, which they dubbed the Northern Isles, are remarkable. Resting 117 feet deep on the seafloor off the Orkney Islands, this 12.2-meter pressure vessel packed in 12 racks with 864 standard servers. It was powered entirely by the local grid's renewable energy, wind, solar, tide, and wave. And crucially, it went from the factory floor to fully deployed operation in under 90 days. It absolutely proves we can aggressively scale capacity without straining traditional municipal grids. But the thermal efficiency was the real triumph here. Land data centers usually operate with a PUE around 1.55, but the Northern Isles vessel? By utilizing heat exchanger plumbing adapted directly from submarine designs, they piped seawater through radiators on the back of the racks and hit a near-perfect PUE of 1.07. Plus, it achieved a perfect WEU of exactly 0, saving millions of liters of fresh water. So, how do we tenant electrons into tokens sustainably moving forward into this off-grid future?
Well, we know the current grid is maxed out, and subsea thermodynamics actually works. Remember, capital will always route around roadblocks to maximize intelligence output. If we're going to build these trillion-dollar AI factories without collapsing our municipal resources, extreme off-grid engineering is absolutely the key. To sustain this exponential economy, our physical infrastructure must migrate to these resilient, lights-out environments that actually harmonize with planetary physics. It's such an incredible shift. We are effectively taking the most advanced cognitive technology humanity has ever built and plunging it into the darkest, most ancient environments on Earth just to keep it running. As we solve the physics wall, how will the fusion of nature's deep-sea thermodynamics and artificial intelligence completely redefine the future of human infrastructure? I'll leave you with that thought to ponder on how we intertwine nature and computation. Thanks for jumping into this explainer with me. Keep learning, keep questioning, and I'll catch you next time.